So that was a really long video, the last one, but you know, we had to do it to derive this thing properly. And now we want to examine what happens as we, so what happens to to this equilibrium as we change endowment E2 and keep E1 fixed. Right, so before we were saying that, oh, E1 is equal to E2, but now we're going to ask, okay, well, what should be happening as we change E2? And to examine this, right, because all we're asking is kind of a local question, right? We're asking a question about change, so we should bring in derivatives to figure things out, right? And we just really want a qualitative answer, and a quantitative answer is not completely useful, but we want to know the behavior of the market, and we want to know if mathematics can tell us something about the behavior of the market. So using differentials, we're going to take those old equations. So go back and look at the equations that we did have, and we're going to take the differentials of all those equations, right? And if we want to maintain an equilibrium, right? So as we change E2, the equilibrium is going to change a little bit, but our equations will stay steady, right? So we want to say that, well, as we do that change, the differentials are not going to change, right? So the differential of the first equation is alpha over 1 minus alpha. The derivative of that thing with respect to the x1 variable will just be u1 double prime of x1, and I multiply by the differential x1 minus p. Now let's take the derivative, the partial with respect to the y1 variable, and we should get u1 y prime of y1 dy1 minus u1 prime of y1 dp. Right, so this is the derivative of that with respect to p, and that's going to be equal to 0. Right, so this is the differential, and I believe this should be a u double prime, because this is the differential of that thing with respect to the y variable. So that's equal to 0. Similarly, we write down the differential for consumer 1's utility constraint, x2 dx2 minus p u2 double prime y2 dy2 minus u2 prime of y2 dp is equal to 0. Now the rest of the equations were all linear, so it simply linearizes the rest of the equations. So we have p dx1 plus dy1 plus x1 minus 1 dp is equal to 0. So this was the income constraint for player 1, but and we would normally write the income constraint for player 2, but it turns out that those 4 equations that we had for the income constraint and the amount of supply in the system of x1, of good 1 and good 2, those are actually redundant. So we can remove one of those, and we're going to remove the income constraint for person 2 because it's already implied by those equations. So we end up with the last equation, of course, is dx1 plus dx2 is equal to 0, which means as I change x1, change the amount in good 1, then I have to change x2 by the same negative amount. And we also have dy1, because the endowment 1 is staying fixed, we're assuming, dy2 is equal to e2. And that's our system of equations, and it's linear, right? Now the IFT tells us, the inverse function theorem tells us, that we may compute all partials at the equilibrium if we can solve this system. Right, so basically what we're saying is that, well, everything, oh, this should be dE2, sorry. Everything here, we're going to say that E2 is the only free variable in this system. So E2 is the only thing changing, and therefore we can take partials of everything, all these values, P, X1, X2, Y1, Y2, with respect to E2, or the change of E2. So let's do it. So first we note that this equation is going to tell us that dx2 is of course equal to negative dx1. And this equation tells us that dy2 is equal to de2 minus dy1. And substitution will yield so in some sense we're doing we're just doing elimination through substitution, and that'll yield, well, we'll get 3 equations now and 3 unknowns. That's the process of substitution. So we get alpha minus over 1 minus alpha u1 double prime of x1 minus alpha over 1 minus alpha u1 double prime of y1 minus u1 prime dp is equal to 0. And this should be dx1. Don't forget those differentials, dy1. And then we've got alpha over 1 minus alpha dx1 plus dy1 plus alpha minus 1 dp is equal to 0. Right, so I didn't change the x1s here. I'm just going to change the x2 and y2 differentials. And so that only changes the function coming from the utility function, from maximizing utility for the second consumer. So I have u2 double prime of, right, this was at equilibrium, right? So in fact I know that at equilibrium this is alpha and this is alpha, right? And at equilibrium, x2 is 1 minus alpha. I have dx1 plus alpha over 1 minus alpha u2 double prime of 1 minus alpha dy1 minus u2 prime of 1 minus alpha dp, and that's got to be equal to alpha over 1 minus alpha u2 double prime of 1 minus alpha times de2, that little differential. So a little cramped here, but that's the system of equations that you get. I just lost the entire screen. It happens sometimes. So scrolling back up. Okay, so that's the system of equations that you acquire. And so multiplying this by scalars, so this is a system of 3 equations and 3 unknowns, so multiply each equation by scalars, right? Doesn't change anything. Well, we get a system like this. You know, we can put this into a matrix, and after doing some nice substitutions, we have R1, which is some function of alpha, R1 of alpha, minus 1 minus alpha. Here we're going to have alpha 1 minus alpha, negative 1 minus alpha squared. So that's the first and second equations representing that first and second row. And then R2 of 1 minus alpha, negative R2 of 1 minus alpha, and minus 1 minus alpha squared over alpha. So it's good to know where these come from, but of course this is, so this is dx1, dy1, dp. But actually setting this up yourself is kind of, an arduous task. But you should be able to do something like this if you have enough time and enough coaxing. That's the whole point. And we have DE2 here. So those are all of the constraints, and here R I of z is a function that we've set equal to negative z ui double prime of z divided by ui prime of z, and this is called the arrow Pratt measure of relative risk. So this is just a measure of risk in the system. So we have this system of equations, and we've got a bunch of zeros over here, so that means that we probably want to use Cramer's rule to solve for this, to solve for dx1, dy1, and dp1. So using Cramer's rule, so we use Cramer's rule to solve for my differential x1, y1, and p in terms of dE2, but when I do that, that tells me the derivatives, and so I acquire the following rules for the derivatives. I have dx1 dE2, right, is going to be equal to negative, again we have to do substitution to make this not look atrocious, 1 minus R1 of 1 minus alpha square all over d. We have dx2 dE2 is equal to, and this is of course at the equilibrium, R2 of 1 minus R1, 1 minus alpha square all over d. We've got dp dE2 is equal to R1 R2 over d. So actually, I mean, in the simplified world, these equations are actually really nice. 1 minus alpha R2 times R1 times 1 minus alpha plus alpha, all divided by d, and then d, this should be y1, y2 dE2 is equal to 1 minus 1 minus alpha R2 R1 1 minus alpha plus alpha all over d. Where, of course, we have to specify what R1 and R2 are. Well, R1, we're just setting equal to little r1 of alpha, which is, of course, greater than 0. And R2 is equal to R2 of 1 minus alpha, which is greater than 0. And D is equal to 1 minus alpha square over alpha R1 plus 1 minus alpha R2, which one can verify that this is also greater than 0. So that's great. So now that we have these derivatives, we can ask, well, as I move around numbers, right, as I change E2, how is everything else going to change, right? So a couple of observations, right? So this is what you do at the end of this analysis, is observations. Right? So that if we increase E2, then so we're going to increase endowment 2, right? Then the price of good 1 relative to good 2 increases, right? Because this dp over de2 equals r1 r2 over d, everything here is positive, right? Everything here is positive, and so as I increase E2, I get a higher relative price. And consumption of good 2 by consumer 1 increases. So that's dy1 de2, right? And of course this is also all positive, right? So you can check and be like, oh well, this is entirely positive. So that means, so this is a really interesting behavior, is that if I increase the amount of stuff that I bring to the market, that guy 2 brings to the market, right? Well, the price of good 1 is going to go up. The relative price, right, is going to go up. So that's saying that in some sense, because E1 is scarcer, right, it has a higher price, and because E2 is more abundant, it has a lower price, right? But also because it has that lower price, we would maybe think that the consumption of good 2 increases as well, and it does, which is very interesting.